these data, done the resemblance matrix using Euclidean distance and drawn up PCA. And you can see here some fairly clear patterns in the location of the samples. There's a gradient for primarily to do with depth going this way, and a second one going this way, that is primarily to do with hydrocarbons, and the severely polluted samples are splitting off. Over to the MDS, start with the data, square root, resemblance matrix using Bray-Curtis, and then the MDS and the separation of the polluted samples is very clear here, with all of the others merging together in a tight cluster or tight grouping. Now, in the previous video, I looked at how we can ask the question or answer the question, are the patterns in the biota reflecting those in the environmental data? And when we've got two resemblance matrices, we can use relate to get a correlation coefficient that measures that relationship. And using permutations, we can test whether that's significant. Now, I've got another question. The biota actually consists of 3 taxonomic groups, and one of those might be more strongly or less strongly correlated to the environmental data than the biota as a whole. So I want to take this resemblance matrix with the environmental data and look at how it correlates with the other taxonomic groups. Okay, that's a task for second stage or 2-stage analysis. So click. And what we're looking at here, which I think is the common situation, is multiple matrices. So I've selected the 4 matrices I'm interested in here. Bio, which is all of the taxa, crustaceans, mollusks and worms. And then just hit OK. Is there a message just to do away with the way I've labelled the spreadsheet, the worksheet, so we'll just ignore it. And we get a matrix here of correlations. Now, as you would expect, the bio complete matrix is well correlated or highly correlated with the individual crustacean, mollusk and worm matrices. There's not a great deal of difference evident between any of the correlations of the environmental matrix to the others. They're all about 0.6. To get a visual representation of this, we can go over to MDS, and I always like to see dots on there. So from the MDS, the environmental data is sitting well away from the others, and none of those, as we saw in the matrix itself, is particularly closer to or further away from the environmental data than the pooled biota or any of the others. So that's one use of second stage analysis. It's where you've got a set of resemblance matrices and you want to look at the correlations among them to see how well the patterns in one are reflected in patterns in the other. Another situation in which we've used it is where we've got essentially the reverse of this. We've got one set of biotic data and then we have 3 sets of environmental data: water chemistry, sediment chemistry and hydrological variables, and we can see which of those sets of environmental matrices the biota is most closely related to. There's another way in which I commonly use second stage analysis. When looking at the biological data, it's common to transform the observations. In this case, I've done a square root transform. In other situations, people would do often a logarithmic transform with the idea of downweighting the particularly abundant species so that the rarer species have some role to play in the patterns that we look at. But that does raise a question as to how much the transform is actually changing the patterns that we see. And so one way of looking at that is actually to do a second stage analysis. So if we look over here, I scroll down a bit, I've got the resemblance matrix for square root transform data. Down here I've got resemblance matrix for the untransformed transformation, log transformation, and then, in a sense, the ultimate transformation, presence absence. And we can do a second stage analysis to see how similar these are. So I'm going to start with the untransformed, over to second stage, and then I've set bio, this is the square root transformed, presence absence, fourth root, and log root. And off it goes, this error message comes up again, no consequence here. And again, it's easier to look at these if we plot it out as an MDS. And I'll put some points on here. So you can see that the untransformed data is most similar to the square root, fourth root, log, but then you get, as you might expect, a fairly big change when we go across to the presence absence. So it's really saying the choice here of square root, fourth root, or log is not making a huge difference. The major choices are when we go from untransformed to transformed with one of these, or then go on to presence absent. And the second stage analysis is a nice way of looking at that, and also it's an easy way to illustrate it for others. Okay, another video here. This time I've got to work with Primer, because I can input these kind of matrices into Primer, but not into a package like PAST, P-A-S-T. And what I'm going to look at here is non-metric multi-dimensional scaling and how it works. Because as this is a permutation-driven procedure, it can be a little tricky to understand exactly how it operates. So what I've got here is a matrix showing distances between some major Australian cities in kilometres. So this is a distance matrix. Clearly a small number here means the two cities, Sydney and Canberra, are fairly close together, 300k, whereas a larger number here, 4,000, is looking at the distance between Broome and Adelaide, which is obviously quite a long way. Now, the data I'm going to use today will be from two sites, this one here, driving distances, and this one here, Australian air distances, which is provided by the Australian government. So back to Primer. Now, ordination methods such as PCA, principal components analysis, principal coordinates analysis, and multi-dimensional scaling use a distance or resemblance matrix. Now, in some cases, we're looking at a distance matrix, where naught means the two items are exactly the same, in the same location, and a large number means they're further apart, or a similarity matrix, which is interpreted the other way, with similarities or resemblances. Small numbers mean that the things are dissimilar, and large numbers mean that they are more similar. In this particular application, Primer, it will recognise distances or resemblances and treat them appropriately. So, what does NMDS do? The first thing it does is it does not work with these actual distances. What it does is it goes and replaces these with ranks. So first of all, it'll find the two locations that are most similar, two sites or samples, and tag them with a 1. So that's the 305 here. And then it will scan through the matrix looking for what the next smallest distance or the next largest similarity, which is going to be this one over here, 755, and I'll tag that with a 2, and it will continue. What's the next largest one? That's 895 down here, and so on. And we will end up with all of these distances replaced with ranks. Now, in doing that, we lose some information, obviously. The Canberra and Sydney are 300 k's apart. Melbourne and Adelaide are 750. And Sydney and Melbourne are 895. If we rank those 1, 2 and 3, we're essentially saying they are equally distantly apart, which is not correct. We're losing some